Application and models. In this section, we're going to do some application problem uh, where we use this exponential and log function. So these are the some application scenario like growth, decay, and compound interest. Our goal is to solve word problem basically. So this is one exponential function, as you can see here, p of t equal p0 e to the power kt. This is just the notation. We just denote this, we just use p for the population, and k, if k is positive, then we can use this model for population growth, where p0 is the population at the time 0, meaning starting time. Pt is the population after time t. T is the amount of the time. K is the exponential growth rate. So whenever you have a population growth problem, we can use this model, this function. This is the graph basically for the exponential growth, and we can use the very similar type of thing for compound continuous interest calculation. We used to use this A, which is future value equal P times e to the power RT, but we can also use the very same model. P of t represents the amount of the money principal after time t. P0 is the initial amount invested. T is the time in years. K is the interest rate compounded continuously. So let's say you would like to find out the growth rate, the value of k, and doubling time t. Then we can use this formula. It's basically here p of t is double than p of 0. So I'm going to put p of t equal 2 times the initial amount, and then you can cancel this initial amount, so it's irrelevant. It's not something you have to be worried for the doubling money. So what is the k? Just take ln of 2 equal ln of e to the power k times t. Ln and e are inverse, so they will just cancel out. It gives you k times t. That's how we get k times t equal ln of 2, and then we can solve for k, or we can solve for time. I'm using small t here, but here is the capital T. It doesn't matter. It's the same thing. Time. This model here represents a model of limited growth. When you try to plot the graph of this function, it will show you the limitation here using the horizontal asymptote. If your time is infinite, this graph is going to approach y equal to a. And the name of this function is logistic function. Okay? This is the model for exponential decay because there is a negative sign here. K represents the decay rate. There is one terminology we use quite often in application problem, that's called half-life. Half-life means its amount of time. The half-life is the amount of time it takes for a substance to decay to half of the original amount. So let's say original amount is this much. How long does it take to make it half? That time is called the half-life of this substance. Okay, this is the graph for the growth. This is the graph for the decay. Okay, you can find the decay rate for the half-life by using the same idea, which is the double or half, and then you can find that rate or time, whatever you need to find. Let's look at some examples. Let's say this is question number 1. It says in 2012 the population of a city was 5.74 million. The exponential growth rate was 3.41%. So initially the initial population was 5.74 million. The growth rate k is 0.0341. This is 3.41%. So that's a 0.0341. Now we know the model, which is population after time t is initial population e to the power k times t. So find the exponential growth function. This is the function. It's 5.74 e to the power 0.0341 t. So that's the function we're looking for. So 5.74 e to the power, there is a power here, e to the power 0.0341 t. That's the exponential function. The population of city, estimate the population of city in 2018. So we started 2012, so the time difference is 6 years. So we use this function, we put t equals 6 and do the calculation. So just go to the calculator, find e to the power 0.0341 times 6 years from 2012 to 2018. Take e to the power that number. Where is the e? E to the power, where is the power? That number, which is, now I have to type it again, 0.0341 times 6. So I'm going to put that thing inside the parentheses. That number times 5.7. That would be the population after 6 years, which is 6.99. So round it to the 1 decimal place as needed. So it would be 7 million. 7.0, which is 7 million. Okay. Find when will the population of the city be 8 million. So now put 8 million here and solve for time. So that means the population is 8 and then equation is 5.74 e to the power 0.0341 t. So divide both sides by 5.74. So take ln both sides, ln of this number, and that will be ln e is the, they are inverse. The leftover would be 0.0341 t. Divide both sides by 0.0341. That will give you the time. So you just have to type this one, which is 8 divided by 5.74. Take ln of that value, and then divide that by 0.0341. That is the time, which is 9.7355. Round to the 1 decimal places, so that would be 9.7 years. Okay. The doubling time is about, doubling means the very same problem, but here this is 2 times this, and then you need to find out the doubling time. You can also use this thing we just already discovered. T doubling time, t is k times t is ln2. So just divide ln by k. So remember, this is the original function, p of t equal p of 0 e to the power k times t. Double 2 times p of 0, then initial. So this p of 0 and this p of 0 is gone. So ln of 2 divided by k is your doubling time. So what is the k? Rate is 0.0341. So just type ln2 ln2 divided by 0.0341. That gives you time for the double, which is if you round to the 1 place, decimal place, so it is 20.3 decimal place. Okay, let's do one more question. Okay, suppose that 16,166 is invested at an interest rate of 6.6% per year, compounded continuously. Find the exponential function that describes the amount in the account after 2 years. So the function is, we already know the function actually, compound continuous function. This is the function with, no. Yeah, this is the function, p of t equal p of 0 e to the power kt. That's the compound continuous. So the amount is e to the power k times t. So suppose that's 16,166 invested. So this is 16,166. Interest rate, which is this k, is 0.066. Compounded continuously. Find the exponential function. So this is the exponential function, which is 16,166 e to the power 0.066t. That's the exponential function. What is the balance after 1 year? Put t equal 1 here and use the calculator. So 0.066 and e to the power that value, to the power 0.066 times 16,166. That would be the value after 1 year, which is $17,268.95. $68.95. And then what about the balance after 2 years? After 2 years, the value would be, as you can see, it's a t times 2, so 0.066 times 2. So type e to the power 0.066 times 2 and times it by 16,166. That will give you the balance after 2 years, which is 18,447, and then the cents, it's 16 cents. If you round it to the 2 decimal place, 0.16 cents. So balance after 5 years, that's the very same thing. E to the power, 0.066 times 5, that's a 5 years. It's a 1.39 times 16,166. It's a $22,486.39. $22,486.33. No, 39 cents. And for the 10 years, it's e to the power 0.066, so 0.66, because you have to multiply that by 10, times it by 16,166, and that's a $31,277.85. $31,277.85. Okay. And the doubling time means $16,166 becomes 32,000, and then just double it. And there is another formula too for the doubling. It's just basically ln2 over k, which is ln2, type ln2, divide this by the rate, which is 0.066. That's a doubling time, which is 10 years, 10.5 years. It's a double one after 10.5 years. Okay, that's all for this section.